Then now we're given this question which they say if the limit as as n approaches infinity of a of n exists, then it is what? Unique. So given that this is our p q. So even though we know that if we're given that this limit exists, right, then it is unique, we're supposed to assume that this limit is equal to two different values, can be L1 and L2, it can be L and M. And then at the end, we show that those two are equal. So many may confuse it for this one, right? You see, right? So make sure you don't. So if you're given it, if it is given to you like this, you should use contradiction. But if they say it is unique, that's when you can use the approach which I'm about to show you here. So we are going to say proof so I'm going to suppose the hypothesis, right? So, but when I suppose we are saying that L, your A of n exists, right? The limit is n approaches infinity. So I'm going to suppose that it is equal to two different values. So I'm going to suppose that the limit as n approaches infinity of A of n is equal to n, and the limit as n approaches infinity of the same limit of the same sequence is equal to what? Or the same function is equal to m. You see, right? So since it is like that, right? So now I can take them one by one and show. So I can say since the limit as n approaches infinity of A of n is equal to L, this would imply, right? Again, I'm saying that it exists. Then I must write the definition to prove that this is true. They exist, and I will call this n, since I'm talking about the value of L, I'll call this NL or N1, it's up to you, which is an element of a natural number, right? This would occur such that we know that for all n should be greater than n, right, of L. Then this would imply that the absolute value of A of n minus L would be less than E over 2, right? And I write since I check the other one, limit as n approaches infinity of A of n would be equal to m, which this would imply that we know that there would exist a positive integer n, but this is for m, right, which is an element of a natural number, so it's a positive integer, such that we know that here for all n should be greater than nm, and this would imply that the absolute value of A of n minus m will be less than E over 2. You see, right? Then now I may take this, since I have n of L and n of m. So I'll let n be equals to, so I'll take here and say, since this is unique, right, I'm saying that there's no any other number other than that. Instead of min, I'll take max, because I'm saying there's no any other number like that, so it is unique. So I'll have L here, it's n of L and n of m. So the other one I took mean, because I say that I may take this as the smallest positive integer, but they may arouse other integers, right? See, I'm saying that there won't be any other output for this input, strictly with that one input, right? That's what's called a function. A function should, one input should produce one output. So now this, we know that they're greater than 0, right? So, because it's an element of a natural number. So now I'm going to say then, since I've already spoken about this and this, then now I must prove that it is unique. You see, right? So I must show that they're equal. For me to show that they're equal, I must subtract this and arrive to E. Then this will be equals to L minus, then I add A of n and subtract A of n. By triangle inequality, we'll have this. And we know that this is less than A over 2 plus A over 2. And this is equals to A. Hence, or thus, the absolute value of L minus m is less than A. Hence, if, so I can just copy the question. Hence, if the limit as n approaches infinity of A of n exists, then it is unique. Right? Which means that L is equal to m. So that will be it for this proof.